Hi, I'm going to be talking about dimensions and why in the world are we even talking about this? Well, it appears as we look out of our eyes that we see three dimensions out there uh, for up, down, right, left, and back and forth, three dimensions, and then there's time. And we have a lot of indications that there's a lot more dimensions than just those. So where are they and what's in them is partly what we're going to be dealing with here. So let's go back and try and do some science here to set the stage for what's going on. I'm going to go to this picture here, and it shows a spiral galaxy, the Andromeda galaxy. Now, this was discovered 1920s, 1930s, somewhere in there. So we've known about it for a long time. It was a cluster of stars, and the optical telescopes finally got to have enough light gathering capability so we could discern that the stars that we saw there actually were clustered together into galaxies, and we're in the Milky Way galaxies with hundreds of millions of stars, and the Andromeda galaxy is the closest one to us, and that has hundreds of millions of stars. So an obvious thing that people did was they said, well, this looks like it's spinning. And if it's spinning, let's just take a look and see about the dynamics of spin. So we'll plug in some numbers for the average mass of a star, and that'll generate a gravitation that'll attract each of the other hundreds of millions of stars. And we'll start it spinning. And what happens? Will the gravity be strong enough from all these stars to keep it clustered together? And the short answer is no. This thing would fly apart. But it clearly is sitting there, and we see many, many of these, billions of these out there as we look. So this leads to the question of, well, what's holding it together? If it's being held together by gravity, then there's got to be more matter out there than we can see. So the idea was to come up with something called transparent or dark matter, dark meaning we can't see it. And the estimates that we have now are that we've been studying 5% of the universe comprised of mass and energy, and dark matter comprises another 27%, meaning that we're missing 68%. What's the other 68%? Well, the other 68% is due to the observation that all of these stars and galaxies are moving away from one another, and they're being pushed by the expansion of space itself. So that requires a huge amount of energy. In fact, most of the energy, and we can't see it, so we call it dark energy. So we've come to the conclusion that 5%, which is what we've been studying for 500 years, of the mass and energy make up our scientific knowledge, and 95% encompasses dark, 27% dark matter, and 68% dark energy. In other words, we're really at a loss as to what's going on. Now, if we have all this other dark matter and dark energy, where in the world is it? Well, one obvious way to deal with this is to say it's in other dimensions. We can see three spatial dimensions around us. So if we have 5% of the mass and energy, then that's 1/20th is in three dimensions. So in 60 dimensions, we have all of the mass and energy. That's one way to go think about it, but it comes up with a lot more dimensions. I'm going to cut to the chase and say the right answer is we actually have another 24 spatial dimensions, and then there'll be two time dimensions. Yes, that's right. It's two, not one time dimensions, but we'll get there. So where else did we come up with this in looking at things? What other indications that we have that things were requiring this sort of stuff? So I'm going to just go back to I'm just going to switch screens in a second, but what happened was there was a lot of activity with people all through the 20th century in trying to reconcile these different things. And in particular, in 1962, Richard Feynman, a Nobel laureate, gave a series of lectures at Caltech when he was trying to develop a theory that would encompass both gravitation and quantum mechanics. And in doing so, what he uncovered was he postulated there would be a particle called a graviton that was exchanging gravitational energy with different things. And he said, well, one thing we've discovered from quantum mechanics is that this can have an attribute called spin. So he said, is it possible to construct a spin equals zero quantum gravity theory? And he concluded the answer was no. He then went ahead and said, well, what if the spin were one? And he concluded the answer was no. But when he got to spin equals 2, and spin only comes in integer multiples, he concluded that it was possible to have a self-consistent gravitational quantum theory, but he couldn't figure out what it was. So we go ahead to the 1970 timeframe, and Claude Lovelace at Rutgers is doing some fundamental work. So he postulates that because of the need for the spin equals 2 graviton, that he'll construct a theory for what are called bosons. A photon is an example of this. The Higgs boson is another example. So for these bosons, they'll be effectively what we would call today vibrating strings. And so he has these strings in this in oscillating, and he realizes that in 3 spatial dimensions, he ends up with a lot of problems. His theory is all kinds of inconsistencies and infinities in it. And he did the radical thing of saying, well, what if I increase the number of dimensions? Because I've got all these problems. And he kept increasing it at 4, 5, 6, 7, 8. When he got to 26, all of a sudden, all the inconsistencies disappeared. In other words, you could have bosons that were in a spin equals 2 quantum gravity theory, and they were bouncing all around these 26 dimensions, and there were no inconsistencies, and everything appeared to make sense. Now, that's truly amazing. If you think about it, he of course was ridiculed by everybody as this is the dumbest thing I've ever seen. But we'll come back to that and see who has the last laugh. Now, what I'm going to do is go off here and do a digression again to something. Down here, what we see is the periodic table of elements. So this comes out of a lot of work in the for several hundred years since the Renaissance, going up into the 1860s, and we have this periodic table of elements. So up here in the very top left is hydrogen, and over here in the top right is helium. And the difference is that hydrogen has an atomic number of 1, or it has 1 proton in it, 1 entity in its nucleus with positive charge, and helium has 2 protons in it. And so it has atomic number 2. The hydrogen has no neutrons, which is the bulk of all hydrogen, but it has things called isotopes. And so one isotope is called deuterium, where we have 1 proton and 1 neutron. And so the atomic number is 1, but the atomic weight is 2. The proton and the neutron have roughly the same weight. So that's different. And then we have a second isotope, tritium, that has 2 neutrons and 1 proton. So the atomic number is 1. There's only 1 proton, but now there's a total weight of 3. Helium over here, for example, we have 2 protons, but we also have 2 neutrons. And so its atomic weight is 4. So we went from a weight of 1 to a weight of 4 over here. And so it goes. There's this regularity running through this table of elements. And this is a great accomplishment. We see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18 rows here to encompass all of these different things. And down on the bottom, we have 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let me check that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 times 2. These are special elements down here. So the point is we have this clustering of 18. Now, we're going to do a digression and go off to some math that occurred. A lot of people aren't aware of this, but this is amazing math. And here we are here with something called the periodic table of finite simple groups. So the mathematicians, not to be outdone by the chemists or the physicists, decided to study symmetries. And the study of something that's symmetric is called a group. So an example of a group is if I have a square that's laying on a flat surface and I rotate it 90 degrees, it comes back to looking exactly like a square, but it's just rotated 90 degrees. And I can rotate it 4 times and I'll come back to where I started from. So that's an example of a finite simple group involving rotations. And the mathematicians, instead of using the word atom, they use the word simple. So these are simple groups. These are the atoms that make up all the possible symmetries. And so they've constructed this table here, and I want to observe that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 12, 13, 14, 15, 16, 17, 18 types of possible symmetries. Now, isn't that interesting? We saw in the table down here for the periodic table of elements that there's 18 things down here, which raises the question of, is there some relationship between these possible symmetries? These are all the possible symmetries that could come up here. These involve rotations, translations, scalings. We can double everything or have everything. And there's others that are much more sophisticated. So there's 18 types of these, again, finite simple groups. And then if we look down here at the bottom for the finite simple groups, we see something funny, which is these are finite simple groups that don't fall into this category of the 18 classes. And that's interesting. So it means that the study of symmetry results in things that aren't symmetric. They don't fall in any category. They're called sporadic. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 here, 13 down here. That's 26. 26. Well, that's interesting. We just got through hearing about 26 dimensions for these bosons that are running around in space. Okay. So that leads us to putting all this together into a picture. And the picture looks like this. The universe that we're in actually has 26 real dimensions, okay? There's 24 spatial dimensions and 2 time dimensions, and those are all real, but they're all paired. So we have a real and then what's called an imaginary part, something that's multiplied by the square root of -1. So all 26 of these dimensions are paired. So there's really only 13 complex dimensions here. That's why this word symplectic is in there. It's a tip-off that we have to remember that they're paired. And of the 13 complex dimensions, one of them is time. So time shows up in the left and the right here. As we can see there, we see time showing up down here. And that means that we have 12 complex dimensions or 24 real dimensions. And what goes with this is now there's a huge amount of structure in this picture here, because what we see here is that there are 10 dimensions for what we would call matter. So we see 3, which I've labeled X, Y, and Z, and then time gets multiplied by c, the speed of light. Speed of light is 3 times 10 to the 5th kilometers per second. So now we have time multiplied by a speed that gives us meters per meters, but it's multiplied by the square root of -1. So that's the one thing that makes time different, is these other 3 dimensions, X, Y, and Z, we can go back and forth, right and left, up and down, but time, we're stuck right here in the present. And when the past is receding behind us, the future is coming up on us. We can't go backwards or forwards in time, or can we? We'll see when we get to this. Similarly, over here, we have another 4 space-time dimensions, which are the ones that we have here, we see around us, but they're all rotated by 90 degrees. That's typically what people talk about when they multiply by the square root of -1. There's a 90-degree rotation in the complex plane. And for those that know anything about this, it means something. And for those that don't, just keep that in mind. So we end up with 3 imaginary spatial dimensions here, and then 1 real time dimension. So apparently time here, which is minus CT, is in fact a real thing here, and for what we call dark matter. And what happens over here is there's another 6 dimensions here that are what are called compactified dimensions. There's 2 3-dimensional subspaces here that add up to 6 in real dimensions, and then they're each multiplied by the square root of -1 to give us another 6 over here. And finally, down here at the bottom, or we could flip the picture around and put it at the top. Down here at the bottom, we have another 2 3-dimensional subspace, 1 single 6-dimensional subspace here, linking all of these things. And so what's going on here in this picture, to make things interesting, is there's magic numbers that are occurring. We saw back up here, when we go back up to our table here of sporadic groups, here's the 18 here, and here's a different picture of it here that mathematicians have cooked up that has a certain structure to it. These 26 sporadic finite simple groups apparently have a role in the 26 dimensions that we have down here. We don't know what that is. Also, we have these 18 dimensions here in the compactified dimensions, and the 18 apparently has some sort of tie-in to the 18 categories or classes here that we have for the finite simple groups coming across here. The other thing that happens here that's really bizarre is we have matter here, and matter is made up of atoms. So the atoms live forever. But the atoms themselves are made up of electrons and a nucleus, and the nucleus has protons and neutrons in it. When we look at the nucleus, the protons and the neutrons are each made up of things called quarks. And in fact, the quarks, there are 3 quarks that go into each proton and each neutron, different types. And when we look at the quarks, there's 3 types of subquarks. There's 3 subquarks of different types that go to make up 1 quark. And the subquarks are it. We're at the bottom. So the subquarks make up the quarks make up the protons and neutrons, and so forth. And that different is there is no electron. So here all we have are subquarks, and the subquarks are what they are, but the subquarks, again, they live forever, just like the subquarks over here live forever. And these things create what we would call souls, or sentient entities. And those things live forever, and they have a curious linkage whereby when something happens over here, say something is born, like a human being, something from over here in the dark matter side, which is called the soul, links up with this body, incarnates in it, and then stays with it. And then when this body dies, ends up going back over here and regrouping, and goes back and forth, back and forth. We don't really know why. We think the reason this occurs is that this leads to greater growth, intellectual growth, and knowledge happening with this coupling occurring here than anything else. The other thing to keep in mind here about the dimensions is down here, we're showing a picture that shows the hierarchy of science, with physics, chemistry, and biology. So physics deals with these fundamental entities that are these subquarks that actually are a cluster of 10 vibrating strings. The strings vibrate and they create a resonant ball of energy, a little jelly bean, little soft squishy ball of energy. And that ends up giving us all the particles that we have. And that leads then to, through these atoms, of the creation of the periodic table of elements, all the elements that we saw. And that in turn leads into biology, with the notion that the atoms form into these proteins, and there's some notion of bioelectricity here. Whereas on the dark matter side, the subquarks are actually only have 5 strings, not 10 strings, and they're vibrating. So they're not vibrating as much, but they create what we would call the right subquarks. This leads to the chemistry of the subquarks, which actually looks like a fern tree, we'll see in a second. And that leads into the biology, which is having a sentient entity. This entity is either active, sentient, because it's got some thermal vibrations that are exciting it, or it's in the depths of space, and then it's quiescent. They're typically found in tubes that can be hundreds of kilometers long. Now, here's an example as we go down here, for example, of an electron. Electron has, again, 10 of these vibrating strings around it. They resonate to create this energy, which is actually resonating into a torus. There's a hole in the middle of the electron. Even though the electron appears pretty round, there's a little hole here. And lo and behold, the electron is covered with little blocks of what are called information. Now, this really is information. If we look at the blocks here, we see that they're all stacked up like this. And if you look on the surface of the blocks, you'll see a snake, which would be a wave of information moving from one place to another in this storage mechanism. Here's a much more complicated wave down here. And what we discovered in doing this was that space itself is quantized. Space itself is made up of discrete compartments. The discrete compartments form a foam that make up what we call space. The foam that we're dealing with here, it has on the walls of the space compartment these blocks of information. Now, these blocks of information are constantly sending out signals, scanning, and they're doing so in these other compactified dimensions. So they're sending out signals that are trying to detect, is there any change? Is there any change? Is there any change? And if there is a change, then the algorithms that are embedded in the wall, in these algorithms, in the blocks of information, those entities will end up acting accordingly, and they can not simply do the coordination here, but they can control what happens in the 4 space-time dimensions for matter and for dark matter. They can control what happens there. They're not simply doing calculations here. And so this leads to this picture here with information controlling everything everywhere throughout all this hierarchy. Another thing to keep in mind about this is, if we go down here a bit, here's a boson, for example, a a photon would be an example of a boson, and it also is a torus, okay? So these are different cross sections of this, and the information is flowing on the outside of this torus here in different ways, and so it goes. And if we go further down here, we have other pictures showing things that are going on. Here's a picture of these subquarks for dark matter, and they're starting to form this fern, and then after a while, they rapidly create this incredible entity here, which is sentient, which creates what we call the soul. And all of this is encompassed in this book down here by Ron Cowan, The Path of Love, The Future of Buddhism as a Science. And it includes a lot of observations that Ron did over the years. So the thing that we have to keep in mind is, where else did we find this stuff? Well, if we go look into, for example, the Yoga Sutras of Patanjali, which were written down around 0 AD, but were clearly oral. They consist of 195 sutras. Each sutra is maybe 3, 5, 7 words in Sanskrit. So the whole thing could be memorized by a single person. So it evidently was oral for millennia. We don't know how long. But the Yoga Sutras are broken down into 4 books. The first book is dealing with how to learn how to meditate, how to settle your body and settle your mind so that you can avoid all the distractions around you and go into deep meditation. And the second book, that covers maybe 50 sutras. The second book covers another 50 on meditation and what to do there. Then the third book deals with what comes out of this, and in particular, it talks about various powers that you can come up with as you meditate, and those powers involve, in fact, accessing some of these compactified dimensions so that you can levitate. For example, Marco Polo went on the Silk Road in 1275 to China and back. And while he was on the Silk Road, he stopped off at an oasis, and the Pasha who was there had 2 of his yogis meet with Marco Polo, and they were both floating about 3 feet off the ground. They achieved this by going through this process of deep meditation. Another thing that comes out of this is clairvoyance, that you can see very far. You can see out into the depths of space, and you can see out down into the microcosm, down into what are atoms, or down into the actual compartments of space itself. That's what clairvoyance, clear seeing, means for you. What comes with this when you combine the two is, this is how Ron Cowan was able to do these sorts of pictures that we have down here, where, for example, he has a picture here of an electron, but the electron actually is moving all over the place and is jittering as well, and he's able to stop it and to construct these pictures here. But if you didn't have this capability, you'd just see a blur here, and it would just be bouncing all over the place. And so it goes. So the Yoga Sutras of Patanjali are one indication of this. And what does Patanjali say about meditation? He says, well, basically, you're sitting here and you're looking out through your eyes. Conceptually, there's some little person inside your head that's doing this, and you should think of this as a movie. So I'm here looking out at a movie. So now let's suppose that I'm actually able, through deep meditation, to imagine that I'm in a seat in the movie theater looking at the movie. So I've now stepped away from the movie. I'm not in the movie. I am in the movie, but I'm sitting out there in the audience watching it. And this, where is this movie theater? Well, it's in this 26-dimensional space. That's what's going on here, is that we start to see these other dimensions that are here, and we're able to sense this. and we sense a much greater linkage to everything being linked through this notion of information that's scanning things everywhere. I think I skipped over one thing. These six-dimensional spaces evolve. They themselves, there's on YouTube many videos showing these things spiraling, rotating, doing all kinds of things. Another thing to keep in mind, another tip-off here is the following: that in this compactified space here, we have three holes in the six-dimensional space. In this six-dimensional space, we have four holes, and down here in this one, we have 8 holes. So that suggests that the 3 holes here link up with 3 out of the 8 holes here. 4 holes here link up with 4 out of the 8 holes here, and one of the holes here links up with another dimension here in the 6 dimensions. So the way to think about this is that we have not 18 full dimensions, but we have a linkage between them. We have 8 holes. We have 18 dimensions, so the 8 holes basically link together 8 of the dimensions, so that we only have 18 minus 8, or 10 dimensions. 10 dimensions. Where in the world have we seen 10? If you know anything about Judaism, the Kabbalah talks about the tree of life with the 10 Sephiroth. The 10 Sephiroth consist of 3 very mystical entities. That's probably these 3 dimensions here in this underlying Calabi-Yau manifold here. And the other 7 are here between the 3 and 4 that are down here in these other subspaces. So that's a tip off that 26 really is the right number. A different indication that this is correct is the obvious one, that we had Jesus of Nazareth, who was an amazing individual, and he talked about a Father, a Son, and a Holy Spirit. Well, if he's incarnated in these 10 dimensions, he's here as the Son, the Father is probably up here, and the Holy Spirit is probably over here. Again, this is just as suggests this. There's no proof of any of these things, but it makes a lot of sense. Another tip off that this is correct is the following: that in physics, there's a basic what's called standard model for particles. And when you look at the standard model for particles, what you discover is that the electron has 2 other particles associated with it that appear to be linked to the electron in some way. We have 3 holes here in this manifold here. And what that suggests is that the electron actually has 2 other resonances, 2 other resonant energies because of these 3 holes, that in total mean that there's only 1 electron and 2 resonances. So the number of fundamental particles associated with electron is really only 1 with these 2 resonances. And so it goes. Similarly, over here, there's 4 holes, and so we end up with these subquarks that over here that would have potentially 4 entities mirroring a particular type of subquark, and really there's only 1, and the other 3 are all resonances of what's going on here. Underlying everything is the notion that we learned from Einstein, that mass is proportional to energy, E equals mc squared. And we also have learned from Max Planck that energy is proportional to frequency, E equals h nu. So if energy is proportional to frequency and mass is proportional to energy, then mass and frequency are proportional to one another. And that suggests the following: that the dimensions that we're dealing with here, in fact, there are these 18 Calabi-Yau manifold dimensions, but each of these other sporadic subspaces, each of these 26 finite simple groups down here themselves have extra dimensions. And so these extra dimensions are probably linked one to each of these different dimensions that we have here in our 26 real dimensional universe. So for example, if we have the three dimensions here for space and time, there's another three that are linked to it out of this category of these sporadic groups. And these have many dimensions to it. One of them, which is the largest one, has 47 times 59 times 71, or 196,883 dimensions. So it's a tip-off that if we were able to change our frequency, meaning we would change our energy, that we could go up and down in dimensions here, and we could effectively become very stealthy. You should think of this as the following, that suppose we can't do this in 26. I'm going to do a simple example where we live in a two-dimensional space. We'll call it flatland, and it's actually in a three-dimensional space. And so if we raise our energy, we can move up above the flatland space, and we can look down and see everything that's going on in flatland, but nobody can see us because we're up above everything else, or we're down below everything else looking at everything. And this is a standard technique that shows up again and again for how people have disappeared, and there's no way to go find them. And with that, we're going to close. I want to thank everybody for the time, and we're glad to take any questions. All the best. Bye-bye.